These slides are about polarization of light. Separation of light waves with electric field vector oriented only in single direction is called polarization of light, or this is process in which light and other radiations are restricted to vibrate in a single direction only. In our previous discussions, we described the transverse nature of light, and polarization is firm evidence of this transverse nature. An ordinary beam of light consists of a large number of waves emitted by the atoms of the light source. Each atom produces a wave having some particular orientation of the electric field vector E, corresponding to direction of atom vibration. The direction of polarization of each individual wave is defined to be the direction in which the electric field is vibrating. This direction happens to lie along the y-axis. However, an individual electromagnetic wave could have its own electric field vector E in the yz plane, making any possible angle with the y-axis. Because all directions of vibration from a wave source are possible, the resultant electromagnetic wave is superposition of waves vibrating in many different directions, and the result is an unpolarized light beam. The direction of wave propagation in this figure is perpendicular to the page. The arrow shows a few possible directions of the electric field vectors of the individual wave, making up the resultant beam. At any given point and at some instant of time, all these individual electric field vectors add to give one resultant electric field vector. The most common technique for producing polarized light is to use a material that transmits waves whose electric field vibrate in a plane parallel to a certain direction and that absorb waves whose electric field vibrate in all other directions. In 1938, E. H. Lane discovered a material which he called polarite that polarizes light through a selective absorption by oriented molecules. This material is fabricated in thin sheets of long-chain hydrocarbons. The sheets are stretched during manufacture so that the long-chain molecules align. After a sheet is dipped into a solution containing iodine, the molecules become good electrical conductors. However, conduction takes place primarily along the hydrocarbon chain because electrons can move easily only along the chains. As a result, the molecules readily absorb light whose electric field vector is parallel to the length and allow light through whose electric field vector is perpendicular to their length. It is common to refer to the direction perpendicular to the molecular chains as the transmission axis. In an ideal polarizer, all light with electric field vector E parallel to the transmission axis is transmitted, and all light with electric field vector E perpendicular to the transmission axis is absorbed. When an unpolarized light beam is reflected from a surface, the reflected light may be completely polarized, partially polarized, or unpolarized, depending on the angle of incidence. If the angle of incidence is zero, the reflected beam is unpolarized. For other angle of incidence, the reflected light is polarized to some extent, and for one particular angle of incidence, the reflected light is completely polarized. When light is incident on any material, the electron in the material can absorb and re-radiate part of the light. Such absorption and re-radiation of light by electron in the gas molecule that make up air is what causes sunlight reaching an observer on the earth to be partially polarized. You can observe this effect called scattering by looking directly up the sky through a pair of sunglasses whose lenses are made up of polarizing material. Less light passes through the certain orientation of the lenses than at others. In this diagram, the scattered light traveling perpendicular to the incident light is plane polarized because the vertical vibration of the charges in the air molecule send no light in this direction.